you should have some intuition connecting the forces that are applied to things as providing energy. And so we're going to talk about the connection between forces that act on things and giving objects energy. And we're going to do it through this concept of work. Now I realize we use this term work when we're talking about homework or jobs that people have, but in physics this has a very specific definition. Shouldn't be a surprise, and it's going to be a mathematical definition, but it's still tied to then the force that's applied to something as it moves along some distance. That's going to be our work. And so we're going to sort of get a feel for it and then look at it, how we actually set up equations associated with work. So here's sort of the intuition. We have a block and we drag it. We have a force that's applied. Maybe there's friction, maybe there's not. And it goes along some distance that we're calling the displacement. It goes from point here to a point here. And the work that's done by this force in this instance is just the size of the force times the displacement. That's the work that's done. And so first, the units, we should say something about units. Work has then units of newtons times meters, which we could rewrite Newton being our force, so mass times an acceleration, meters per second squared, and then times another meter. So that's the unit of work, newtons times meters, which we can write in fundamental units like this, but this is what we call a joule. Okay, so our units of work are joule, which you may know is a unit of energy. So work is a form of energy. Okay, so this is our definition of work. And, well, not quite our definition. This is just sort of our intuition about work. But there are other forces that are acting on this block. For example, I have weight that's down. And the weight isn't doing anything to contribute to the displacement, right? So this weight, the work done by the weight in this case is equal to 0. Similarly, the work done by the normal force normal, the work done by normal is also equal to 0. So somehow we need to connect this into our understanding of work. And so what work is it's the force either in the direction of the displacement that, in other words, the component of force that's along our displacement, which gets rid of these two. So for example, if we have a force like this, and I'm going to focus really on constant forces like we have here. So there are really two cases here. I'm going to focus on constant force, and then eventually we're going to need to get to changing forces. But for right now, we'll just stick with a constant force. So let's say we have a constant force in this case, but now it's up in this direction. The force is like this. The block still moves like this. There's our displacement. So the work that's done in this case would be, we really want the x component of the force, would be Fx times d. In other words, the component of force along the displacement, so in the same direction as the displacement. Or we could have a situation like this. We have a block on a frictionless, magical frictionless surface. It starts at rest, we let it go, it obviously slides down this way, that's the displacement. But its weight, right, the component of weight is the one that's along the plane is what's driving it down. If we notice, we have a normal force here, and in this case, the force normal, because it's perpendicular to the displacement, doesn't do any work. But the weight does, and what we can do is say, we can have another way to calculate this, to say, hey, I can take dy times my force, and in this case, the work is equal to force times dy, or it is the component of displacement in the direction of the force. And both of these will give you the same thing. You can do the calculation in either way. And what this is really describing is taking these two vectors and multiplying them in a special way, a way you already know about. It's saying, let's take our work is equal to F dot the displacement. And if you remember, our dot product is the magnitude of the force times the magnitude, it's these two vectors, times the cosine of the angle between them. So let's check to make sure that agrees with what we have. So here's the angle between them. Notice that Fx is equal to F cosine of the angle. So that could equal F times D times cosine of the angle. Yep, that's a dot product. Over here, this right here is the angle between the displacement and weight. Right? Weight is down, displacement is that way. That's like that. But dy, if we look, is equal to d cosine of the angle. So this becomes force times d times cosine of the angle. The same expression, which is exactly what we have here. That is what our dot product gives us. That's the type of vector multiplication that gives us the component of one of the vectors times the other times the angle between them, or the amount the two vectors line up, which is what we want. Work is a measure of the force in the direction of the displacement. Notice we can have a positive work or we can have a negative work. You can have a situation, for example, where you take a block, right, and you hold it and you lift it up. So you lift it up. Then if we look, you've got a normal force that's up. And if you lift it up at a constant speed, that normal force must be equal to the weight. So the work done by the normal force, if the displacement is up, so that's the direction of the displacement. So the work done by the normal force, in this case from your hand, is greater than 0 because these are lined up, and the angle between them, phi, between these two, the angle between them is 0, right, because they line up, but the angle between this and the weight is 180 degrees, so the work of mg in this case is negative. It's less than 0 because it's really in the wrong direction, okay? So work doesn't have a direction, but it can be positive or negative depending, you can think of it as whether the force is helping or not helping. In this case, the weight force is not helping. Your hand's having to go against that, and that's the work that it's putting in.